So today's lecture number 9, is on radio resource management, and today we're going to have an introduction to radio resource management, and then we're going to look at some important aspects of radio resource management, namely admission control, packet scheduling, link adaptation, power control, and interference. Okay, and we will be giving you an introduction into each one of these topics. Okay, each one of these topics by itself is quite complex, and we'll be just giving you an introduction into each one. So let's start off by looking at an introduction to radio resource management. So the first question you might ask is, what is a radio resource unit? Okay, well, when we talk about a radio resource unit, it depends on the technology that you are referring to. So, but generally, a radio resource unit can be defined as given here. It says here, RRU is a set of physical transmission parameters necessary to support a signal waveform transporting end user information corresponding to a reference service. So this is the official definition of the word RRU. But basically, what does it mean? It means the resource that you allocate to a user. Okay, so if you're looking at in the first generation mobile communication system, the resource that you allocate to a user is a frequency band, and the user has access to that frequency band for the duration of the call. In the second generation mobile telephony system, the resource we allocate to a user is not only a frequency band, but we also allocate a time slot within that frequency band. When we move to a third generation CDMA based system, the resource we allocate to a user is a frequency band, a 5 megahertz band, and within that 5 megahertz band, we also allocate a code and a power level. Okay, so these make up the resource unit. So these are the set of physical transmission parameters that are needed to specify a radio resource unit completely. In a fourth generation mobile communication system, the resource that you allocate to a user is called a resource block, and we talked about this in most of the previous lectures. And we already know what a resource block is, so just as a revision, I'll explain what it is. So when we talk about a resource block, we are basically saying it's 180 kilohertz wide, and it lasts for 0.5 of a millisecond. So in that time, that 180 kilohertz is made up of 12 subcarriers and 7 OFDMA symbols if you're using the cyclic prefix, okay, and the normal cyclic prefix. Now within each of these resource block, there are 84 resource elements, and within a resource block, all of them are transmitted with the same modulation and coding scheme. And so these are concepts that we looked at, and depending on the bandwidth, okay, obviously the higher the channel bandwidth that you have, the more resource blocks that you can have. So this lecture looks at how do we go about allocating these resource blocks in an efficient manner to all of the users. Okay, so the title of this lecture is Radio Resource Management, and basically in any radio network, the 4 important parameters that you have are the capacity. Capacity refers to how many users can we carry at any one time. The coverage is the geographical coverage area. The quality is in terms of the quality of the service the user is obtaining, and efficiency is how efficiently we are using the resource that we have. Okay, so essentially the RRM mechanisms are needed for efficient utilization of our interface resources. So we have all these quality, efficiency, coverage, capacity. Now with radio network planning, and radio network planning is the topic we're going to cover, and in radio network planning we can get a reasonable mapping between capacity, coverage and efficiency. Okay, but you can't get a perfect match. To get a perfect, and radio resource management is a mechanism that is continuously running, and it's usually implemented in software in various nodes of a network, and it is able to get a better match between these four quantities, these four KPIs associated with the mobile network. Okay, so in summary, why do we need radio resource management? Radio resource management is needed to essentially manage and optimize the utilization of the radio resource units, and to ensure that each service or each bearer or each user is provided the relevant quality of service that they've subscribed for, and try and increase the network capacity as much as possible. Now, what are the tasks that are associated with radio resource management? Okay, there are many tasks. We already talked about power control. Okay, so when we talk about power control, we refer to ensuring that all users transmit at the minimum possible power level, because everyone's transmission could be causing interference somewhere else. And also, if in the point of view of UE, if you minimize the power level, you also maximizing battery lifetime. Handover, okay, we've already had a look at handover a little bit last week. We said that as users move across cell boundaries or towards the edge of the cell, we may have to hand over users. We also have to hand over for traffic reasons. And the third important task associated with RRM is call admission control. Now, this is when you have a new call coming in, should you add this user or not? And the other aspects of RRM are congestion control or load control. So when your system goes into an overload, how do you deal with the situation? And packet scheduling becomes one of the most important tasks in 4G, not so important in 3G, but in 4G, RRM becomes very important because everything is transmitted in the form of packets. So if you look at these 5 different RRM techniques, you can classify them into 2 groups. So one set of power control could be classified as connection-based functions. So you have to perform this on a connection by connection basis, and each connection can be treated a little bit independent. But the other functions are functions that you have to do network-based functions. That means you've got to consider all the other users into account as well. So if you look at LT-RRM, we see that some of the LT-RRM mechanisms are done in layer 1, some of them are done in layer 2, and some of them are performed in layer 3. Okay, so we've already had a look at the LT protocol stack. So there are some mechanisms which are referred to as semi-dynamic mechanisms because they are mostly involved during the setup of data flow. So when you set up a bearer, you have to perform. So layer 3 ones are these ones over here. These functions over here, if you look, these are functions that such as admission control, pause management. When you set up a call, all of those are performed when a call is set up, whereas most of the functions that are in layer 1 and 2, which are these functions here, these functions have to perform dynamically throughout from 1 millisecond to 1 millisecond. So every TTI, we need to perform dynamic scheduling, we need to perform link adaptation, we need to deal with hybrid ARQ and so forth. Okay, so all these entities here in the all these RRM entities have to interact with each other. They're not independently. So you could have packet scheduling has to interact quite well with link adaptation, and these also have to interact quite well with the hybrid ARQ manager, which is responsible for retransmission of packets that are arrived in error. So and these take many inputs. Okay, so we've already talked about these inputs in previous classes. So we have the CQI, channel quality indicator, that comes in from the UE. the UE sends a channel quality indicator, and that is used for downlink transmission. It also sends a rank information. It sends an ACK or a negative acknowledgement for the packets that it was received, and these are all used for both link adaptation as well as if you get a negative acknowledgement, it goes to the hybrid ARQ manager, which has to retransmit the packet that was received in error. Apart from that, you also have buffers. Okay, you have buffers in the transmitter and the receiver, and buffer information is also used for packet scheduling purposes. And we also have to know what sort of quality of service associated with each user. So users with high quality of service are more likely to get, bearers with high quality of service, real-time bearers will get a high priority for packet scheduling compared to non-real-time bearers. Okay, we just look at admission control. So what do we mean by admission control? It's a process by which the node B decides whether a new user request should be accepted or not. Okay, so we have algorithms that are running within the eNode B, and these algorithms receive requests from UEs, and they look at the current situation in the network in terms of the current bearers that are there, what is the quality of service associated with the bearers. If we accept this new request, what sort of impact will it have on the network? Okay, will we be able to, first of all, service this request with the quality of service that they are requesting, and second of all, will the other users who are already on the network, will they be affected if we were to accept this particular new request? Now, in terms of the quality of service profile for an EPS bearer, we looked at this a couple of lectures ago, and we saw that there are a couple of parameters. There's something called allocation and retention priority, and there's guaranteed bitrate, uplink and downlink guaranteed bitrate, and there's also quality of class indicator, QCI. Okay, so all of these information is used to decide if we should accept a UE into a network. Okay, so this was the table we saw earlier. Okay, now in some of these slides you have a reference right at the bottom saying Hallmark 2009. So that's the Hallmark text that's on UTS Online. So it's table 8.1 from that text. We've seen this table before. It specifies the 9 different quality of service, 9 different QoS class indicators starting from 1 to 9. We saw that the first 4 are for guaranteed bitrate, and the last 5 are for non-GBR. And we also had priority, so some of them had higher priority. So in this case, you can see that an IMS signaling has highest priority of 1, followed by conversational video, and then for some unforeseen reason they've put real-time gaming as the third highest priority, and so forth. And you also have delay budgets. Okay, so basically what we have to do is we got to make sure that our packet is out through the network within this delay budget. Okay, and we also have packet loss rate, so we should try and ensure that we maintain this packet loss rate associated with that quality of service profile. Okay, so for some services we can afford to lose packets. For example, conversational voice, it's okay to lose 1 in 100 packets, but when we have conversational video, we might want to only lose 1 in 1,000 packets, and so forth. Okay, so all of this information about a particular UE's bearer is then used to ensure not only for admission control to make a decision whether a user should be accepted, but also in subsequent packet scheduling decisions, we have to make use of these parameters for each bearer. Okay, we move on to the second and probably the most important function of the RRM, that's packet scheduling. So what do we mean by packet scheduling? Well, we know that if you look at the downlink side, in the E node B, there will be many buffers. Okay, into each buffer, we have a user's packets coming in. Okay, and these packets have then got to be transmitted on the downlink to the various users. And we essentially, how do we transmit them? We allocate different resource blocks to different UEs. So whatever packet is in a UE's buffer is then transmitted on a specific resource block. Now, in order to make that decision, we need two things. One thing is we need a packet scheduling algorithm that's in the E node B that makes a decision of how to allocate resource blocks to different UE packets. Okay, so just in summary, scheduling refers to the process of allocating resources for UEs to transfer their packets which are sitting in the serving E node B buffer. And this one is performed at it's a layer 2 function. Okay, so if you go back and look at the previous slide that we saw on the different layers, the dynamic packet scheduler is a layer 2 function in LTE. But even though it's a layer 2 function, it has to interact with other layer 1 and layer 2 entities in order to make this decision. Now, packet scheduling decisions are performed every millisecond or every TTI, and we allocate a pair of resource block or PRBs to the user. Okay, and just how does it work? Basically, each user in the network will be sending back a CQI report, okay, to the E node B, and the E node B will use the CQI report to determine which user has the highest metric, and that metric is calculated by a packet scheduling algorithm, highest metric on each resource block. So the user who has the highest metric on a particular resource block is allocated that resource block. So what could be the situation is one resource block could be good for one user, but it could be bad for another user. So the one which it's good for will be allocated the resource block. So this way we can overcome the effect of multipath fading. Okay, so that's one of the. Okay, so overall, if you look at a block diagram of this system, we have in the E node B we have number of buffers. So each UE could be having multiple buffers associated with multiple bearers, and also on the uplink within the UE there are buffers with packets waiting to be transmitted on the uplink. So both on the uplink as well as on the downlink, the E node B has to make scheduling decisions based on the various factors such as how many packets are waiting in the buffer, what sort of quality of service is associated with this user, are the user's packets getting closer to the delay threshold which we saw on the table earlier, are users' packets getting more lost and the packet error rate is getting close to that threshold level, and also priority of packets and so forth. Okay, so a whole lot of information is being used, and in our research work we've also developed some of our own packet scheduling algorithms, and we sort of simulated them and tested their performance as well. So the basic idea, the whole reason we have packet scheduling, why do we have it? Well, we want to ensure that we maximize the cell capacity. We want to try and transmit as many users' packets as possible. We want to fulfill the quality of service requirements for all the connections, and we want to make sure that we keep some resources for best effort application, which may not have any strict QoS requirements. Okay, so I talked about channel dependent scheduling earlier. Just to clarify what this means, in case you've sort of forgotten this. basically in this particular example, you can see two users, okay? And the yellow part represents the channel. How do channel measurements look for user 1? Okay, so remember, channel measurements have two aspects to it. There's a frequency aspect, because you're making channel measurements across different resource blocks, and there's also a time aspect, because you're making channel measurements every TTI represent. So you can see on certain resource blocks the yellow is better, and on certain resource blocks the blue is better. Okay, so this is just an example with two users, but we could have a situation where we could have 10 or 100 users. So associated with each resource block, you could have a user who has the best channel condition. Okay, so channel dependent scheduling is, we are making scheduling decision based on the channel condition for a particular UE. Okay, so if you were to take that graph we saw earlier and we were to make it into a one-dimensional graph, this would be an example. Okay, so you have channel quality of user 1 is the dark line, and the channel quality for user 2 is the dotted line. Okay, so you can see in this time slot here, user 1 has a better channel condition, so we will allocate this resource block to user 1. Okay, and similarly in this resource block here, in this time slot here, in this TTI value, you can see that user 2 has a better channel quality, so we allocate the PRB to user 2 and so forth. So based on channel dependent scheduling, basically means we are using the channel condition of the channel to make scheduling decision. Now with channel dependent scheduling, you can see that we can improve the overall throughput by up to about 40%. If we didn't use channel dependent scheduling, and if we use channel dependent scheduling through computer simulations, they have proved that you can get 40% improvement in terms of average throughput in the system. And that's the graph that's shown here. And this is from the Hallmark text 2009. Okay, so again, this point is about the PRB, physical resource block. So physical resource block essentially means two resource blocks. Okay, because we always allocate two resource blocks or a pair of resource blocks at any one time, and this is referred to as a PRB. Now there are many packet scheduling algorithms, round robin, max rates, proportional fair, MLWDF, exponential. Now I don't want to be going into each one of them, so what I've done is all the slides pertaining to these algorithms, I've put them in the appendix of this presentation, and you can have a look at them. Okay, the second function that we're going to look at is called link adaptation. So one thing that happens in wireless communication is the channel quality can vary very rapidly. Okay, so it can drop by about 30 dBs. So how do we deal with this situation? So within a few milliseconds, the SNR, the receive signal to noise ratio, can drop by up to about 30 dBs. So this is why we use link adaptation in LTE to overcome these kind of problems associated with the rapid change of instantaneous channel quality. And we perform this in time domain. And how do we do it? Well, when we have a good channel quality, the basic idea is when you have a good channel quality, you try and use a high order modulation scheme so we can get a high data rate. And when the channel quality drops, like when you have a deep fade, you use a low order modulation scheme. Okay, and it's also referred to as adaptive modulation and coding. So how does it work? Okay, now there are two terms in link adaptation and power control. They sort of mean similar things, but they're quite different. In 3G, we use power control quite a bit. but in LTE we use link adaptation in the downlink and we use power control in the uplink. So how does power control work? Well, imagine that your channel is varying as shown in the okay, so basic idea here is if this is how your channel is varying very rapidly, you can see that when your channel quality is good, you can transmit at a lower transmission power. Okay, so you can see at this point here, where you have a good channel quality, you can afford to transmit at a lower power. Whereas when the channel quality rapidly drops, okay, and you have a deep fade, then you have to increase the transmit power to compensate for the channel. Okay, now because there are these measurements that are being constantly sent on the uplink, you can in both directions, you can use that to decide on the power control. So in the case of 3G, for example, the node B informs the mobile to increase and decrease its transmission power very rapidly. Okay, but throughout the time we keep the modulation scheme constant. Okay, you can see modulation scheme is kept as constant as possible. Now what we do in link adaptation, which is also referred to as rate control or AMC, we keep the transmit power constant. So you can see the transmit power is kept as constant as possible, and as the channel quality goes up and down, we use different modulation schemes. Okay, so when we have a good channel quality, like somewhere up here, in power control we might transmit at a higher power, but in link adaptation we use a higher order modulation scheme. So in the case of LTE, we might use 64 QAM, for example. And when the channel quality is very bad, we might not transmit at all, or we might use the low order modulation scheme such as QPSK. So essentially what we're doing is we are adapting the modulation and coding during the transmission process on the downlink in LTE. Okay, in order to do that, we have to the block diagram. If you look at a block diagram of a transmitter and a receiver, is the signal. Whenever you transmit a signal, you have fading and additive voice Gaussian noise being added, and it arrives at the receiver. The receiver demodulates and decodes the signal. It estimates the channel, and it sends on the feedback channel. It sends the CQI, and the CQI is used to adapt the modulation and coding scheme. In the case of LTE, you only change the modulation and coding scheme. You could also use this model for 3G, because you can say in the 3G case we would change the transmit power. Okay, so the other aspect is that link adaptation has to work very closely with packet scheduler, because these two are quite related functions. Okay, so we have three types of adaptation. We have inner loop link adaptation, where a packet scheduler uses the CQI to determine supportable MCS for a user depending on the allocated resource blocks. And then there's something called outer link adaptation, where you adjust the transmission power and mapping between CQI and MCS based on information such as past HARQ, acknowledge, ACK and NAC messages. And then there's also MIMO adaptation, where you change the based on the PMI and rank indicators, you can change the information, the way you transmit information to a UE. Okay, so this so the key important thing for all of this, both packet scheduling and link adaptation, is this feedback that comes from the UE. So the UE transmits certain reference signals, and the the E node B transmits certain reference signals, and these reference signals are measured by the UE, and the UE then feeds that back to the E node B, and the E node B, based on the information that it's receiving from the UE, it performs both packet scheduling and link adaptation based on these two. Okay, now these CQI reporting, there are two possibilities. you can either have periodic CQI reports or you can have aperiodic CQI reports, and the comparison between periodic and aperiodic is given in this table. Okay, so periodic is usually a very small number of bits because you are transmitting it constantly, but you transmit it every 2 to 60 milliseconds. Whereas aperiodic is something only when it's requested by the E node B, and it can use up to about 64 bits to do a more detailed measurement. Now we move on. Then the third type of RRM, power control. Now power control is performed only in the uplink in LTE. So it's not performed on the, as I said earlier, link adaptation is performed on the downlink. So the main idea of power control is, first of all, you want to try and reduce the transmission terminal power consumption, okay, because you want to extend the battery life. And the second thing, you want to make sure that the received the power spectral density of different UEs at the receiver is approximately at the same level. Okay, and this way you can also avoid the So now again, the equation for power control is a little bit complex. Now I've put a slide here that this is not going to be examinable. Okay, I just want to give it to you as an introduction. Okay, so if you look at it, power control is set by this equation. So you're taking, you are taking the minimum of a couple of things. You're taking the minimum of either the maximum possible transmission power or this term here. Okay, so that term accounts for the number of resource blocks. It accounts for the power that the UE is requested to transmit at by the UE, and it also accounts for path loss and the modulation encoding scheme that is allocated. Okay, so again, just an introduction. I'm not going to go into, I don't expect you to know this for your quiz or your final exam. So so essentially power control does not calculate the absolute power, but the power spectral density for a UE, essentially accounting for mostly for path loss. Okay, in power control, there are different power control schemes. So we have something called conventional power control. So if you look at that equation, when you set alpha to 1 in the previous equation, this the power control has full compensation for the path loss. You can also have fractional power control, open power loop control, and closed loop power control. Okay. And the last topic that I want to look at is intercell interference. So in two types of interference, we have something called intracell interference and intercell interference. Intracell is within a cell. So within a cell, two UEs that are transmitting. Now because each UE is transmitting on a resource block, and essentially because the OFDMA symbols are orthogonal, there shouldn't be any interference. But there is a possibility that however well you design your radio equipment, some amount of transmission could leak over, into an adjacent channel and cause interference. And that results in intracell interference. So intracell interference is usually considered a very small problem because of the fact that we are allocating orthogonal OFDMA symbols to users. But intercell interference is a major problem because the resource blocks that are used in a cell can be reused in adjacent cells. So you could have two UEs, especially in the case that the UEs are at the cell edge, they could be using the same resource block, and their transmission could interfere with each other. So So this is explained by this diagram here. So we have the case where a UE is close to the edge of a cell, and maybe the transmission from the base station, the same resource block that was allocated by this serving cell to this UE might have also been allocated by this E node B to another UE, and you have interference occurring as a result. Okay, so it's a major problem for cell edge users. So usually in most of the intercell interference literature, they distinguish between cell center users and cell edge users. So one of the important things that we use to quantify the interference is the signal to interference plus noise ratio. Okay, so if you try to give a mathematical expression, again, I don't expect you to be able to use this formula. Okay, it's just given to you as background material. SINR is made up of SINR refers to a particular user M on a resource block N. Okay, so M here refers to a UE, and N here refers to a resource block. Okay, so what does it depend on? Well, it depends on the transmission power on that resource block, okay, from cell site L, because there may be many cell sites that are using that transmission power, and it also depends on the channel gain, which is usually given in the form of a channel matrix. Okay, and this here is the sum of all the other cells where they're using the same resource blocks. Okay, so the symbol K here represents other cells from which the same resource block is used. And then this term here is essentially the interference term. Okay, and so this term here represents the receive power. Let me just mark that. So as I said, this term here represents the receive power for user M on resource block N from cell site L. This term here represents the interference because the same resource block N is being used in other cell sites. And this term here represents the noise term. Okay, so this will give you the signal to interference noise ratio, which is an important quantifier of the level of interference. Now, what is the impact of interference? So this slide essentially says when a UE starts to move far away from E node B, what exactly happens? Well, as a UE starts to move away from E node B, the channel gain between the base station and the E node B starts to decrease. And when the channel gain starts to decrease, SINR decreases, because you can see if this term here decreases as a UE moves further away from, then that means SINR also decreases. Okay, and if the SINR decreases, essentially what that means is that the throughput decreases. So we know this to some extent. The further you move away from the base station, the achievable throughput that you're going to get will decrease. Another possibility is when we have transmission power of neighboring cell on a resource block increases. So imagine the situation where we have the UE, you have another UE in an adjacent cell, and the transmission power increases. Well, if the transmission power increases, well, essentially the interference increases, and interference is in the denominator of that equation. And what that means is that SINR decreases. And again, when SINR decreases, the throughput decreases. Okay. And the third possibility that could occur, this one is less likely to occur because usually transmission power is kept constant. But the third possibility is when neighboring cells allocate the same resource blocks to the UE. This is the one that is a problem of intercell interference, because most likely we try and maximize the use of resource blocks, because again, bandwidth is limited, resource blocks are limited. We want to try and maximize the use of the resource blocks. So when neighboring cell also allocate the same resource block to the UEs, then interference also increases, and this interference increase causes SINR to decrease, and hence the throughput decreases. So the impact of all of these phenomena that are shown on the top in blue is the end result is the throughput starts to decrease. So how do we overcome this problem? Well, there are different techniques that are used to mitigate the effect of interference. Okay, how do we reduce the impact of interference? So first, this is, if you look at general literature, if you look at 2G, 3G, 4G technologies, and we say in all of these technologies we have interference. So the question is, how do we overcome the effect of interference? So one technique is called interference randomization. So we might use techniques such as scrambling, interleaving, spread spectrum. All of these techniques can be used to reduce interference to some aspect. Another technique we use is interference cancellation. Okay, so this is where we detect a certain amount of interference and we subtract that interference from the desired signal. Or the other possibility is when in the case that we use MIMO, where we have multiple antennas, we can select the best signal from multiple received signals. And the third possibility, and that's the one we're going to focus a little bit more in this lecture, is interference avoidance. How do we go about avoiding interference in the first place? So this could be done by suitable allocation of time, frequency, and power to your users, so that we can increase the signal to interference noise ratio for cell edge users. Okay, so this is another function that the RRM has to do. Okay, it's an interference control or interference coordination is a radio resource management function. Again, it's based on measurements. Remember, the RRM protocols are receiving feedback from the UEs, and they use this to coordinate the interference. Now, in the case, the only difference here compared to other RRM techniques, we need to know information from our neighboring base stations or E-node Bs. So we have this X2 interface that is there between E-node Bs, and this X2 interface can be used to carry some important interference and scheduling information, which can be used for. So if you know well ahead how your neighboring cells are going to schedule their resources, how they're going to use the RBs, then we can use that to determine how to minimize their interference. So again, interference, ICIC can be broadly classified into reactive and proactive schemes. So reactive is you measure and you perform an action. Yeah, proactive is where you inform your neighbors about the way you're going to allocate resources, so they can be aware of what sort of interference they will get. So one of the things that we use is called load indication. In LTE, this is LTE specific. In LTE, we use something called load indication, which is sent on the X2 interface between E-node Bs. Okay. Now, there is something called a high interference indicator, and that's sent on the X2 interface. It indicates scheduling of uplink cell edge users. So this is only information about your cell edge users that you send to your neighbors, and because it's the cell edge users that are going to cause most of the interference. There's also another thing called overload indicator. This is where you take measurements of the uplink interference plus thermal noise for each resource block from other cells, not on your cell, but you take these measurements from your other cells, and then you classify this measurement into 3 values, either a low value, a medium value, or a high level, and you transmit this value to your neighbors so that they are aware of how whatever they are transmitting is being measured at neighboring cells. And you might transmit this maybe every 20 milliseconds to send this information to your UEs, to your neighboring cells. Okay. So as I said earlier, we talked about reactive and proactive schemes. So in reactive schemes, we make measurements and we monitor the performance. If we notice that the level of interference is getting very high, we might have to take some appropriate action. Okay, so one possible action would be you could ask your UEs to reduce the transmit power, and also you might make packet scheduling decisions. You might coordinate that between cells so as to reduce the interference. And we'll have a look at different ways that this can be done as well. Now, proactive schemes are probably the more easier way to overcome interference. So this is also referred to as interference avoidance, because we want to make sure what can be done to minimize interference. Now, we know that in LT it's possible to set different downlink transmit power per PRB, but one thing is, once we set that, we will try and keep that as constant as possible. Okay. So there are different ways that we can do. We can have an interference avoidance mechanism. So the first mechanism is called the full frequency, and I have diagrams for each one of these, so we probably go into that slide. The full frequency one is probably not a good solution. Frequency reuse 1. Okay, so here we are using the entire resource block, entire bandwidth in each cell. Okay, now this configuration here can probably maximize capacity, but in terms of interference, there's going to be quite a lot of interference between adjacent cells. The other side of it is to use something with frequency reuse 3. So we chop the frequency band into 3 equal parts, okay, and we allocate 3 adjacent cells each part of the band, and we make sure that adjacent cells do not have the same, do not use the same frequency band. The good thing about this scheme, what is the good thing about frequency reuse 3? It's a good interference avoidance scheme, but what is the negative thing about it? Sorry? Less bandwidth, which means, okay, you're reducing capacity because you're dividing the bandwidth into each cell. So what are the other possibilities? So this was the frequency reuse 3. Another possibility that we could use is called partial frequency reuse or fractional frequency reuse. So what we do here is we divide the bandwidth into 2 parts. One part is we use the same bandwidth in adjacent cells, and this is reserved for cell center users. So we use the same cells. For cell center users, we use the same bandwidth, but for the cell edge users, we divide it into 3 parts. And this can be also dynamic, okay? And we run it this way. So this is a scheme which can sort of be used to optimize between capacity as well as interference. So here, what are we doing? Well, what we're doing here is that we're using the entire band in every cell. The only difference we're doing is for cell edge users, we allocate different portions of the band and we transmit them at higher transmission power. Okay? So what this means is, for example, the transmission power for each PRB, but once you set it, you keep it at that. Okay, you don't want to be changing power up and down, but once you can set certain PRBs to be transmitted at a higher transmission power than other PRBs. And that's the idea behind software frequency reuse. Okay, is that clear? Okay. So again, we've got another slide that shows the difference between partial frequency reuse and software frequency reuse. And again, these boundaries between cell edge and cell center can also change. Okay, if you have a situation where you have a lot of cell center users, then you might only have very small bands for cell edge users. Whereas in the case where you have a lot of cell edge users, you might have less bands for less resource blocks being allocated for cell center users. Okay, so this was a quick introduction to RRM. Okay, these sort of slides cover the important ones.